Alright, hello, my name is Camden. We're Team 2, and this is our tactical presentation on human motion detection and tracking. Let me introduce our team. This is Will, our team manager, Mike, our presentation coordinator, Ryan, our webmaster, and Mark, who prepares our documents, and I'm Camden, and I'm the lab coordinator. Our facilitator is Dr. Wen Lee, and our sponsor is the Air Force. Here's a brief outline of our presentation. We'll go through the introduction of our technical topic. We'll go over a brief history of motion detection. We'll go through the different methods of detection and how the technologies that are involved in these methods. We'll go through the different modeling techniques and the algorithms used for these techniques. We'll go through how these can be applied in today's society, and then we'll close up at the end with big questions. To introduce our topic, human motion tracking is one of the many forms of motion tracking. Detecting human activity has become one of the most important forms of motion detection and can be applied in many fields. Developments in different camera technologies and other technologies make different motion detection possible. Here's some brief history on motion detection. Infrared search and track was developed after World War II, and it was used to detect emissions by different enemy aircraft. Motion controllers were developed in the early 90s and were mostly made for game consoles. This is the Sega developed the first actual motion controller that could detect physical movement by the player. This is actually it right here. But it was very unsuccessful because it was very inaccurate. It only had like 8 lasers that could detect the player moving. The Nintendo Wii Remote was released in 2006. It was the first controller that used accelerometers to detect the orientation and the acceleration of the player. It also had an infrared pointing device to detect the player was pointing at the screen. Depth sensing technology was not invented until 2005, but was not released until the public until the Xbox Kinect was released until 2010. And Ryan will go over different methods of detection.
Hi, I'm Ryan. I'm going to be talking about the different ways you can detect people. So there's a variety of different ways that you can essentially transduce a physical signal in order to detect somebody. One way is obviously with sound. You can use an audio recorder to track footsteps and analyze those. You can monitor vibration and seismic activity. When somebody takes a step, they create vibrations, which can then be picked up by an accelerometer or a similar device. You can also use ultrasonic sonar. You can broadcast an ultrasonic signal, which will then be reflected by the environment. And based on changes in that environment, that signal that you receive will change, and so you can track people through your environment. Also infrared. Infrared, essentially you pick up heat energy coming off your environment, so people are easy to spot. You can also use infrared in order to detect depth. All of these technologies have advantages and disadvantages. Some are better than others, and I'm going to discuss those. So sound is an obvious way to do it. When someone takes a step, you can hear it. It generates a broadband frequency, both ultrasound and low frequency. You can analyze both of those. Basically, there's a unique signature that you can look for when someone takes a step, and you can monitor that. This technology works best indoors. Outdoors, you have noise, cars, trees, wind. Anything like that will disrupt your signals. So vibration, you can use this. You can use an accelerometer. The subject needs to be pretty close to your accelerometer in order to pick it up. It's also difficult to analyze. Your readings will vary with where you are. So if you're walking on grass as opposed to concrete, you're going to get a completely different signal, which can make it difficult. However, this has an advantage over sound because it'll work outdoors. You don't have to worry about wind or noise or sounds in your environment, but you would have to worry about vibrations that you might not want, like from a car or from a train. So ultrasonic sonar, as I said, uses a transmitter and a receiver. You transmit an ultrasonic signal, which then gets reflected by your environment. And when someone walks through that, you can detect changes using a computer, which your receiver will pick up. You get a pretty wide field of vision with this. Sound travels pretty far before it degrades, which, as I said, I'm going to talk about infrared next, which is a little more limited. With sound, you can detect moving objects because you can watch the change through your environment. You can develop algorithms to detect that. So infrared, unlike ultrasound, there's no transmitter. You just have a receiver that picks up heat energy that's being emitted by the environment. What you do is you can monitor the temperature changes around your environment. You can also see where someone has been. When someone moves through your environment, you can use that to detect motion. And using multiple infrared sensors, you can detect depth and you can create algorithms to track movement. Will's going to be talking about how Microsoft models it.
Hi, I'm Will. I'm going to talk about Microsoft's method when they developed the Kinect and how this works. The old way that cameras used to track people is they actually start with a calibration pose, and the calibration pose might be something like Da Vinci's Man or like a strongman pose. You would actually stand in front of the camera and wait for it to pick you up. The big problem with, or the way this works actually, is that it essentially, if the frame rate's high enough, it'll know that you to look for a body part in close to the same location it was before, because you can't move too fast. The big problem with this is if it does lose a body part, it's impossible to find you again unless you recalibrate and stand in that pose again. Microsoft decided they didn't like that, and they wanted a robust solution. So they scanned the 3D image and found body parts in a new way. This research actually led to the development of the Kinect SDK that they released. So basically what the Kinect has is it has two cameras, an RGB and an infrared camera. And it'll scan a single input depth image using the infrared camera, which is like this gray image here. And it'll find that. They'll then use a probability theorem to label body parts. They find up to 31 different body parts from head to toe. There would be the colors here. From there, 3D joint proposals are made, and that's also based off the probability. Some joint proposals are joints of interest, like hands, feet, arms, and legs. Others are actually like intermediate joints so that they know, so they can better predict what other joints will be in the future. This is all treated on like a per pixel basis here, but here would be the joint proposals that they found. They also can do things where like, essentially they can focus on the top half like there in this picture, or the bottom half, or full body. So you can do whatever you want with it, really. These decisions are made basically, Microsoft generates hundreds of thousands of realistic human bodies in a ton of poses. They then use a decision forest, which is a group of decision trees. The reason that they do this is because this avoids overfitting one particular decision tree to look for 100% match. With hundreds of thousands of images, they don't need an exact match. If they get as close as possible, it should be good. These would be the decision trees that Microsoft actually used in their paper. The big issue that they were worried about at the time was speed, because you're generating all these images and running them through each pixel through all these decision trees. But since the decision trees aren't overfitting them, it actually works quite quickly, and because they can run each pixel in parallel on the decision forest. When they tested on the Xbox 360 GPU, they actually were doing 5 milliseconds per frame, so they were extremely pleased with that, but that worked. And hand it off to Mark.
Hey, I'm Mark, and I'm going to be talking about alternative 2D models for motion tracking. This model is going to be bipedal, and it's all it is going to be 6 rectangles, one big one for your torso, one for your head, and then 2 for your thighs and 2 for your calves. And all it's going to be doing is going to have an algorithm that's going to do 3 things in a loop. First thing is it has to detect human candidates, and these may or may not actually be humans, but it's just things that are moving. And second, we have to validate, And then third, we have to track that if it is a human in subsequent frames. First part, the input to this is actually the output of a pixel-based motion detector. And that is going to be with non-motion subtracted out. So this man right here is moving and his surroundings are blacked out. Basically, we want to find regions of interest. We're going to call them ROIs. And how we find those, we're going to have a rectangular mask, and we're just going to search the image that this 2D camera is giving us. And if any motion is detected that like reasonably fills up that box, kind of like this guy does, then that's going to be passed on. The mask is scalable, so if you have the box at the lower part of the screen is going to be slightly bigger because that means the person is closer to the camera. So if it's moving away, that means that the person is going to be farther away, so therefore it's going to be smaller. So in this model, it does assume that people are all generally the same height, so it won't really find, it'll have trouble with toddlers and like small adults. Second part is validating. This is where the bipedal model is initialized. They'll do this at each region of interest. We basically just want to determine the position of the model and orientate the legs and the head, because it can find people that are upside down, essentially. But basically, we want to just use a mean shift algorithm to find the pose that best fits the image that in the ROI. And all a mean shift algorithm is just a very old mathematical formula to find the most dense area in a discrete data. And they'll do this with starting with the torso, because that's usually the widest area in the region of interest, and then they'll do the legs, and then they'll move on to the head. After this, the model is refined. If we're working with a human, if it is a human in there, usually it's going to be about correct. Usually, sometimes there's going to be like maybe grass blowing or a shadow that's moving across the frame, and that will just interrupt. Well, it'll have the head maybe be in just a slightly wrong position, so they'll refine that and maybe move it up. Usually it's just vertical spacing that needs to be adjusted. And at this point, this is where any non-human is going to be thrown out. So if this algorithm that runs doesn't reach a certain threshold, then they know it's not like a real human. Lastly, we track the model, and what they do is they use the pose of the model from the previous frame and try to anticipate the movement of that human. Basically, for example, if you have someone that's walking and their leg is out like this, kind of far away from the body, you can reasonably assume it's going to start moving back towards the center of the body, and they just use certain laws to anticipate where the next pose is going to be. And they use that exact same algorithm from the validation phase to just fit the model to the next image that's coming in. So overall, this is it's very efficient and it's a very quick program. It does have limitations because it is in 2D. So if there's a moving person and then there's maybe another larger non-human moving behind it or in front of it, it will not find the human. It'll actually get thrown out in that validation phase talked about earlier. But overall, it is cheap and effective. So I'm going to hand it off to Mike to talk about some applications that are used in the real world and in the future.
Hi, I'm Mike Lazar. Like Mark said, I'm going to talk about some of the alternative applications for this human detection and tracking. One industry that's actually very interested in it is the automotive industry. Their main motivation here is safety, not necessarily safety for people inside the car, but also for pedestrians, cyclists, people outside of the car that might be in danger. So in a lot of luxury cars that are coming out nowadays, they're like BMWs or Volvos or Lexuses. They're putting cameras in the rear of the car, in the front of the car, or both. One of these systems is called Mobileye PCW. That stands for Pedestrian Collision Warning System. This is something that's been installed on Volvos for the past couple of years. what it is there's a camera in the front of the car that's constantly monitoring as you're driving, and it's looking for pedestrians or cyclists that it thinks might be on the path and that you should be aware of. If it finds something that it considers a threat, there is a light in the middle of the dashboard that lights up, and there's a alarm sensor that basically says, hey, pay attention, you might want to brake right now. This is a passive system in that the driver still has full control of the vehicle. The vehicle's all it's doing is notifying the driver. What we're going to see when these things start to get more reliable is they're going to switch over to more active systems where the car might actually start applying the brakes for you as well as notifying you. When you do that, you need a very robust, reliable solution. You can't have false alarms and things like that. So the automotive industry is definitely looking into improving this, and it's something to look out for in the next couple of years. Another application for human tracking is in surveillance and security. They've been using this for a long time now. So if you're in like an airport and you have like hundreds to maybe like 1,000 cameras scattered throughout the airport, you can't reliably be watching all those cameras at the same time. What you need is like sort of a first layer filter that goes through and looks for abnormal behavior. It looks for maybe a person running through a crowd or a person walking through a restricted area. And if it sees something like that, it flags the camera and sends it to a security guard who can assess the situation and take action. And so this is actually more reliable in that if you have people watching these cameras all the time, they're going to get tired, they're going to miss things. But if you have a computer system that's watching them, it's always active and it's always online. And these things are used in airports, subway stations, office buildings, private estates, large areas like this. So some more applications, I'm just going to run through these real quickly. Content-based video categorization. Can you determine if a person is in a frame, if there's multiple people in a frame, what they're doing, whether they're running or standing or jumping or dancing or things like that, and can you use this to better categorize videos for a site like Google. Sports video analysis, motion capture for film and television, gesture recognition for smart devices. For example, they're having a laptop that's coming out either this year or next year, I'm not sure, but you just sit in front of the laptop and it recognizes that your face has entered the screen and it detects your user and logs in for you. That's some of the cool stuff that they're working on with motion detection. So, in summary, we talked a little bit about the history of human detection and tracking, including infrared used in World War II, as well as some of the motion controllers that have been developed in the entertainment and gaming industry. We talked about some of the alternative methods of detection besides just video. You can use sound, vibration, sonar, and infrared as well. We talked about some different ways of software modeling of humans, including Microsoft's new approach that sort of uses joint positioning and classification, as well as a two-dimensional model that Mark talked about. And finally, I talked about some of the applications of human detection and tracking, including the auto industry and in security. So, any questions?
Anyone? Okay, I guess